You are not touching the chair you're sitting in. You have never touched anything in your life. I know how that sounds, but I want to show you why it's true, not as a metaphor, not as a philosophical position, but as a straightforward consequence of what matter actually is at the level where the physics happens. Because the picture your senses give you of the physical world, solid surfaces, continuous matter, objects that are genuinely there, is real as an experience and completely wrong as a description. Let's start with the table. You experience it as solid, continuous, present. You press your hand against it and it pushes back. Your nervous system reports surface, resistance, matter, and all of that is happening. The resistance is real. The surface is real in the sense that matters for navigating the world. But the picture implied by that experience, a continuous mass of stuff filling the space the table occupies, is not what's there. What's there is almost entirely nothing. Every material object, the table, the chair, your hand, everything you've ever called solid, is made of atoms. You know this. But knowing it abstractly is different from really sitting with what atoms are actually like. The picture most people carry is the planetary model. A nucleus in the center, electrons orbiting around it like tiny planets around a tiny sun, clean, visualizable, almost completely wrong. The nucleus is real, and it is genuinely almost incomprehensibly small relative to the atom it sits at the center of. Here's an analogy that gives you the scale, and I want to be clear, this is a teaching approximation, not an exact number, but the relationship it illustrates is accurate. If you took a single atom and expanded it to the size of a football stadium, the nucleus at the center would be roughly the size of a marble sitting on the 50-yard line. The rest of the stadium, everything between that marble and the outer walls, is where the electrons are, not where the electrons orbit, where they are. And that distinction matters enormously because the electrons are not doing what the planetary model suggests. Here's where the picture has to get harder to visualize. Because electrons don't travel in paths. A planet orbits a sun in a path you could trace, an ellipse, predictable, definite, locatable at any given moment. An electron does nothing like this. An electron exists as a probability distribution spread across the space around the nucleus. It doesn't have a location. It has a probability of being found at various locations when you look for it. The cloud of probability you see in accurate atomic diagrams isn't a simplified picture of something more precise underneath. The cloudiness is the reality. There is nothing more precise underneath. When people ask where the electron is right now, exactly, precisely at this moment, the question is malformed. It's like asking what the exact boundary of a cloud is. The question assumes a sharpness that the physics doesn't have. The electron doesn't have a position until you interact with it in a way that forces a position to exist. And after that interaction, it goes back to being a cloud. So what fills the atom? Not electrons in the sense of little balls whizzing around, probability clouds, smeared out quantum possibilities, something that behaves like a particle when you force it to, and like a diffuse wave of probability the rest of the time. The atom is a tiny, dense nucleus surrounded by an enormous cloud of almost nothing, and that's what your table is made of. The nucleus itself deserves a moment, because while the electrons are diffuse and strange, the nucleus is the opposite. Tiny, dense, almost violently compact. Protons and neutrons packed together inside the nucleus with almost no space between them. The density this produces is genuinely hard to hold in your mind. A teaspoon, an ordinary kitchen teaspoon, of nuclear material, pure nucleus with no surrounding electron cloud, would weigh roughly 1 billion tons, not as a rough figure, as an actual consequence of nuclear density calculated from first principles. This isn't exotic matter. This is what the center of every atom in your body is made of. The nuclei inside you right now have that density. They're just so small that the total mass they contribute is the mass you see when you step on a scale. The nucleus is held together by the strong nuclear force. one of the four fundamental forces, and the most powerful one at the scales where it operates. It overpowers the electromagnetic repulsion between the positively charged protons packed together in the nucleus. But it only operates at extremely short range, nuclear distances, femtometers. Get slightly further away, and it switches off completely, which is why the strong force doesn't affect anything at the scale of atoms, let alone the scale of objects. All the mass, almost none of the volume, a tiny, dense core, and then an enormous cloud of almost nothing extending out to what we call the edge of the atom. That's the structure. Now, the question that should be bothering you: if atoms are almost entirely empty space, if matter is a tiny nucleus surrounded by a vast electron cloud with almost nothing in between, why doesn't matter pass straight through matter? Why does the table feel solid? Why don't your feet sink through the floor? The answer has two parts. Most explanations give you only the first one. The second one is stranger and actually more fundamental. Part 1, electromagnetic repulsion. The electrons in your feet and the electrons in the floor carry the same charge. Negative. Same charges repel. As the electron clouds of your feet approach the electron clouds of the floor, the electromagnetic force pushes back. Ferociously, the repulsion kicks in long before the nuclei get anywhere near each other. The clouds interact and resist compression through pure electromagnetic force. This is why you don't pass through the floor. Not because surfaces are touching, because electron clouds are repelling each other with enormous force at extremely short range. Part 2, the Pauli exclusion principle. And this one requires a moment. The Pauli exclusion principle is not a force. This is the critical distinction. Electromagnetic repulsion is a force. Forces can be overcome, push hard enough, supply enough energy, and you can compress matter against electromagnetic repulsion. That's what happens in extreme astrophysical objects. Stars compress under gravity. The electromagnetic repulsion fights back. Eventually, under enough pressure, it loses. Pauli exclusion is different in kind. It's not a force pushing things apart. It's a rule written into the structure of quantum mechanics itself, a constraint on what configurations of matter are allowed to exist. The rule is this: no two electrons can occupy the same quantum state in the same location, same spin, same energy level, same position. The universe does not permit it, not because something prevents it, because the configuration doesn't exist as a possibility. It's not that something pushes the electrons away from each other, it's that the state they'd have to occupy if they were in the same place simply isn't a state that exists. What this means practically: when you try to compress matter, when you try to force electron clouds into the same space, the electrons resist, not just because they repel each other electrically, but because they cannot occupy the same quantum states. They're forced into higher and higher energy states. As compression increases, the resistance is built into the quantum rules themselves. This is why white dwarf stars exist. When a star exhausts its fuel, gravity tries to collapse it. For a white dwarf, a star roughly the mass of our sun, the collapse is stopped entirely by the Pauli exclusion principle. The electrons in the stellar material resist compression not because of electromagnetic repulsion, but because they've run out of available quantum states. This resistance, called electron degeneracy pressure, holds the star up against its own gravity. When the star is massive enough that even this fails, when gravity wins against the exclusion principle, you get a neutron star, where even the neutrons get compressed into their own exclusion-limited states. The floor beneath you is held up by the same principle that holds up dead stars. Put both parts together and you get solidity. Electromagnetic repulsion keeps electron clouds from interpenetrating. Pauli exclusion prevents compression into the same quantum states. Together, operating simultaneously, they produce the macroscopic phenomenon we experience as surfaces that resist pressure, as hardness, as solidity, as the physical world pushing back. Solidity is not a property of matter. It's a property of the interactions between matter. The hardness of a material, diamond, steel, wood, skin, is not about how dense the matter is or how much of it there is. It's about how the electron clouds of its atoms interact and how the quantum states constrain compression. Diamond is the hardest natural material, not because its carbon atoms are especially massive or especially dense. It's because the carbon atoms in diamond form a three-dimensional lattice, each carbon bonded to four others in a rigid tetrahedral arrangement that makes the electron states exceptionally resistant to deformation. The geometry of the quantum constraints produces the hardness. The matter itself is the same atoms you'd find in graphite, which you can smear on paper with your finger. The same atoms, different quantum arrangement. One is the hardest natural material. One marks paper. Solidity is quantum geometry, not substance. I want to tell you what I found astonishing about this, not just as a physicist, but as a person living inside a physical body. Look at your hand, really look at it. You can see it, feel it, move it. It's unambiguously there. And now hold in your mind what you actually know about it, that it's mostly empty space, that the solidity you feel when you press your fingers together is electromagnetic repulsion and quantum exclusion between electron clouds, that the nuclei at the center of each atom are so small relative to the atom that the football stadium analogy barely captures the disproportion. The hand is still there. The experience of it is real, but what it's made of is nothing like what it looks and feels like. I found this not disturbing, but enlarging, like the world had more in it than I'd realized. The hand you can see is a macroscopic summary, an average, a simplification of a quantum reality operating at scales 10 billion times smaller. Your nervous system can't perceive the atomic scale. It wasn't built to. You evolved to navigate a world of objects and surfaces and forces at the scale of meters and kilograms. The quantum world is real, and it's running underneath everything, and it's producing everything you experience, and your senses give you almost none of it directly. That gap between what the senses report and what the physics describes isn't a failure of the senses. It's information about what kind of creature you are. You're a macroscopic being. The atomic world is genuinely outside the range your nervous system was built to perceive. The fact that we've worked out what's down there anyway, through experiment and mathematics and reasoning, is one of the more remarkable things our species has managed. What would the world look like if you could perceive at atomic scales? The solid surfaces would disappear. You'd see vast empty space punctuated by diffuse probability clouds, electron distributions, more like weather systems than objects. And at the center of each cloud, a tiny, intense point of nuclear density. The table wouldn't look like a surface. It would look like a sparse collection of tiny, dense cores separated by enormous distances, each surrounded by a smear of electron probability. Zoom in further to nuclear scales and it gets more extreme. The nuclei themselves are separated by distances enormous relative to their own size. The protons and neutrons inside each nucleus are packed together. That's where the density is. But between nuclei, the void dominates even more completely than between electrons and nucleus. Zoom in further still to the scale of quarks, the particles that make up protons and neutrons, and the story continues. Quarks are bound together by the strong force through particles called gluons, and the structure at this scale is genuinely different from what's above it. And below quarks, we don't know. There may be structure we haven't found yet. There may be a bottom to this somewhere, but there is no scale at which matter finally becomes the solid, continuous stuff our intuition expects. Every scale we've been able to examine shows more structure, more emptiness, more strangeness. There may be no bottom, just structure all the way down. Here's the philosophical position you end up in if you follow this honestly. Everything you experience is physical. The ground you stand on, the walls around you, the body you inhabit, is a pattern of electromagnetic interactions and quantum constraints between structures that are themselves almost entirely empty. The solidity isn't in the matter. It's in the relationships between the matter. It's in the forces and the rules. You are also a ghost. The same emptiness that characterizes the table characterizes the hand examining it. Your body is the same kind of mostly empty quantum structure as everything else. When your hand touches the table, two clouds of electron probability approach each other and repel, and the Pauli exclusion principle prevents the quantum states from collapsing, and your nervous system reports contact, touch, solid surface. None of that is false. The contact is happening, the repulsion is real, the experience is genuine, but the picture it implies, two solid objects meeting at a surface, is a macroscopic summary of a quantum event that looks nothing like that summary at the scale where it's actually happening. This is the thing I want to leave you with. The universe is not what it looks like, not because our senses are broken, they work perfectly for the scale they were built for, but because the scale where the physics actually happens is so far removed from the scale we live at that the two descriptions barely resemble each other. The table is mostly empty space. The hand is mostly empty space. The experience of one touching the other is real, and it's produced by forces and quantum rules operating between structures that are almost entirely nothing. And somehow, out of that almost nothing, comes everything. That's not disturbing. That's the most interesting thing there is.